Hi everyone, welcome to this tutorial about using inverse rendering for volume reconstruction. My name is Telio Vicini and I'm one of the authors of the Mitsuba render. This tutorial is one of several video tutorials that you can find on our YouTube channel. If you haven't watched the earlier ones, you might want to go back to learn about the first steps of using Mitsuba. In this tutorial, our goal is to optimize the parameters of a scattering volume to reproduce the appearance of a set of input images. Most importantly, we will reconstruct volumes while accounting for multiple scattering. This is done by using an algorithm called path-free playback propagation. Please see the paper that is linked in the tutorial for details on this algorithm. While this tutorial works on synthetic data, the same techniques could be applied to reconstruct real volumes from photographs. This could, for example, be used to reconstruct the parameters of a smoke plume or a cloud. As before, we begin by importing Mitsuba and setting the variant of the renderer that we would like to use. Next, we set up a series of sensors that are placed in a circle around the scene origin. Here, we want to optimize our volume using 5 reference sensors. For practical applications, a large number of sensors may be required to achieve high-quality results. To position the sensors, we use the scalar transform class to construct the sensors transformation matrices. We then instantiate each sensor separately using the load_dict function. Next, we set up a scene using an existing volume. The volume is placed at the scene's origin. In Mitsuba, all scattering volumes need to be contained inside of a bounding shape. The shape only serves the purpose of delineating the boundaries of the volume without reflecting light on its own. This behavior is denoted using Mitsuba's null BSDF. In our rendering, we will only see the volume inside of the shape, but not the shape itself. Note that we also set a scale value of 40. This value is used to scale the extinction values specified in the voxel grid that we load from a file. This scale parameter is convenient to globally adjust the density of a volume without having to change the provided volume file. As an integrator, we use a volumetric path-free playback propagation integrator, which efficiently differentiates volume rendering. We use a constant environment illumination to light our scene. We then render synthetic reference images from all our previously created sensors. We can plot these images for our reference volume. For an application to real data, we would instead load previously captured reference photographs. Now we can set up our optimization scene. For this, we take our reference scene and replace the original volume with a uniform volume grid of 16 voxels cubed. To initialize a volume grid from Python, we use the volume grid class. This class is responsible for loading and writing volumes from disk, similar to the bitmap class for images. It can also be initialized from a 3D tensor. Using the dictionary interface, it can directly be passed to the grid volume plugin. We initialize this grid at a low density of 0.002. It's not possible to start optimizing from a completely empty scene because we would never generate any light paths interacting with the volume. This will break the gradient descent optimization process. We use the same scaling value of 40 to scale our extinction coefficients. If we render this new scene, we can see that indeed the volume is now uniform and thin, unlike the dense smoke plume in the reference images. We next create an Atom optimizer and pass the volume's density data as the variable to be optimized. Here we need to call the update function to make the scene aware of the fact that we want to compute gradients. We run the optimization for a few iterations. In each iteration, we update the volume density by backpropagating an L2 loss. We further clamp our optimized extinction values to be between a small positive constant and 1. During rendering, the extinction is still multiplied by our scale factor of 40. The clamping simply prevents our optimization from producing very dense volumes that take a long time to render. It also ensures that the extinction remains positive. Plotting the result after a few iterations, we see that the output is already much closer to the reference than the initialization. We can further improve results by using a coarse-to-fine approach, just as in the caustic design tutorial. To do so, we simply upsample the volume grid using the upsampling function that is provided by Mitsuba. This function trilinearly interpolates the voxel grid values to construct a higher resolution grid. If we run the optimization for a few more iterations, we can see that we can get a pretty good match to the reference. The results here could of course be improved further. One approach would be to add some regularization to improve smoothness, or to penalize some of the haze that forms around the smoke. This tutorial is really only a glimpse of what is possible with Mitsuba 3. You can find the Jupyter notebook with the code for this tutorial in the documentation. Thanks for watching and see you next time.